In January of 2006, the tugboat Valor was pulling a barge off the coast of North Carolina when the weather turned bad. 30-knot winds and 10-foot waves buffeted the Valor, and while she should have been up to the challenge, she instead developed a bad list to port and capsized. The Valor, along with 3 of her crew, was lost. A ship does more than simply sit on top of the water. It balances in it. Understanding this balance is critical for ship's officers. They need to know how to keep their vessel upright in the water. A ship's ability to keep itself upright is called stability. What keeps a ship afloat is the force of buoyancy acting upward against the hull, a force equal to the weight of the volume of water it displaces. But there's a twist. The upward force of buoyancy is not in the same place as the downward force of gravity. The relative position of the two is the essential balance that all vessels must find and is the root of their stability. This video will explore this balance and explain how a vessel rests in the water. By taking the time to understand these principles, officers and sailors alike will better understand the stability of their vessel and how to best keep it safely upright. Working up from the basics, this video will build an understanding of where a ship's stability and trim come from. The following are the standard terms used to describe the hull of a ship, even before it is put into the water. These first few terms are fairly basic. Depth is the height of a hull from the highest point of its main deck to its lowest point. In the other direction, a ship's beam, or breadth, is its width at its widest point. The center line is a vertical plane that runs the length of the ship at the midpoint of its beam, and the baseline is a horizontal plane perpendicular to the center line, located at the lowest point of the hull. The keel is the principal structural member of a ship, running lengthwise along the center line from bow to stern, to which the ship's frames are attached. The lowest point of the keel, or K, is the point from which vertical distances are measured on a ship. K is located at the intersection of the center line and the baseline. The water line is the intersection of the surface of the water a ship is floating in with the sides of the ship's hull. When a ship is designed, the naval architect determines the design waterline, or DWL, that represents the waterline of a ship under full load or maximum draft conditions on an even keel. The forward perpendicular, or FP, is a vertical line drawn at the intersection of the design waterline and the foreside of the stem of the hull. The after perpendicular, or AP, is a vertical line drawn at the intersection of the design waterline and the aftmost point of a ship's hull. For most commercial vessels, this is generally where the rudder post is located. Midships is the horizontal point halfway between the forward and aft perpendiculars, and the length between perpendiculars, or LBP, is the total horizontal distance between the forward and aft perpendiculars. Length overall, or LOA, is the total length of a ship at its longest point. Note that this may be a little longer than the LBP because a ship can extend slightly past the perpendiculars. Distances on board ships are measured in one of 3 directions: longitudinally, transversely, and vertically. Longitudinal is the horizontal direction along the length of a ship. Longitudinal distances are measured from one of 3 places: the forward perpendicular, the aft perpendicular, or midships. Where longitudinal measurements are taken from will vary from ship to ship. Transverse is the horizontal direction across the beam of a ship. Transverse distances are measured port or starboard from the center line, with one written as a positive distance and the other as negative. It is not standard which is which, however, and this varies from ship to ship as well. Vertical distances on a ship are measured upward from the baseline or lowest point of the keel. With these terms in mind, we can now look at how a ship interacts with the water. These concepts are the foundation of stability and trim. What holds a ship above the water is the force of buoyancy, a force that equals the weight of the water the ship displaces. Displacement is the amount of water pushed aside or displaced by a ship when it is floating. A ship's displacement is always equal to the total weight and is measured in tons. Depending on your vessel, ship stability can be calculated in either the metric or imperial system, so you must be familiar with both. Displacement was first understood by the Greek thinker Archimedes over 2,000 years ago. The king of Syracuse had asked Archimedes to determine if a crown he had commissioned was pure gold or if the jeweler had cheated him by mixing in some lesser metal. While he was still thinking about it, Archimedes noticed the water in his bathtub rise as he stepped into it. "Eureka!" he shouted and ran naked into the streets in his excitement. By using displacement, he understood that he could measure the exact volume of the crown. This allowed him to find its density, telling him if the metal was pure or not. It wasn't. Draft is the vertical distance between the waterline and the lowest point of the hull. A ship's draft can be found or taken by reading the draft marks that are welded onto a ship's hull, forward and aft. Tons per inch of immersion, or TPI, is the number of tons necessary to change the draft of a vessel by 1 inch. In the metric system, this is tons per centimeter of immersion, or TPC. Load lines are marks welded on the side of a vessel's hull at midships, showing the draft under maximum safe loading conditions. This mark is called the plimsoll mark. If a vessel is overloaded and its draft is deeper than its load line, it is unsafe and is in violation of the International Load Line Convention. It will be subject to fines or other legal actions, and its insurance is void. Trim is the difference in draft, forward and aft. The trim of a vessel can be found by reading the draft marks on its hull. These draft marks are placed as close to the perpendiculars as the shape of the hull allows. A vessel's freeboard is the vertical distance between the waterline and the highest watertight deck of the hull, usually the main deck. Freeboard is important because it is part of what determines the volume of the space above the waterline. The waterplane area, or AWP, of a vessel is the horizontal intersection of the waterplane and the vessel's sides. The bigger a vessel's waterplane area is, the greater the surface of the hull is that buoyancy will be acting against. For this reason, in the case of two vessels with the same weight added, the one with the greater waterplane area will have a smaller change in draft. As a vessel rolls in the water, its waterplane area increases as long as there is freeboard available to add to it. The larger a vessel's waterplane area becomes when it rolls, the more buoyant force it develops. This is why freeboard is indicative of a ship's reserve buoyancy, or additional buoyancy at larger angles of roll. Longitudinal center of flotation, or LCF, is the geometric center of the waterplane area. The LCF is the point about which the vessel trims. Note that the LCF is not necessarily located at midships. Its location is determined by the shape of the waterplane area and the trim of the vessel. Stability is the tendency of a vessel to right itself. When a vessel is tilted by an outside force, such as wind or waves, and it returns to its original position, it has positive stability. If it does not, it has neutral or negative stability. The center of gravity, or G, is the single point where the downward force of gravity acts. The center of gravity is the combined effect of the position and weight of everything on board a vessel. The center of gravity moves toward any added weight, away from any removed weight, and in the same direction as any shift in weight. On a properly managed vessel, the center of gravity should be maintained on the center line for maximum stability. Because it is a point in three-dimensional space, there are three coordinates used to describe its position. The vertical center of gravity, or VCG or KG, is measured upward from the keel. The transverse center of gravity, TCG, is measured from the center line. The longitudinal center of gravity, LCG, is usually measured from the forward perpendicular or from midships. Understanding where a vessel's center of gravity is located and how it moves is vital for a ship's officer because it is the one property of a ship's stability that they have the most control over. As cargo is loaded or ballast tanks are filled, the center of gravity moves accordingly. How well an officer understands this principle will keep his vessel afloat in heavy weather. Center of buoyancy, or B, is the single point where the upward force of buoyancy acts. It is located at the geometric center of the displaced volume, or the area of hull beneath the waterline. When a ship rolls in the water, the shape of the area beneath the waterline changes. The center of buoyancy is constantly moving to stay in the center of that area. The key to understanding stability is understanding how the center of buoyancy moves. G and B have equal force acting in opposite directions. As a vessel rolls, the distance between the downward force of G and the upward force of B creates a righting moment that returns the vessel to the upright position. A moment is nothing more than a force or weight multiplied by its distance from a particular point. Think of it as a lever. A moment can have a greater effect because the distance increases or because the force increases. In the imperial system, moments are measured in foot-tons. The effect of the longitudinal difference between G and B is trim. Trim is defined as the difference between the forward and after drafts. The opposing forces of G and B across the trim arm create a trimming moment that causes the vessel to trim around the LCF. Keep in mind that the deeper draft of a ship's trim will always be on the same side of the trim arm as the LCG. If the LCG is forward of the LCB, then the forward draft increases. If LCG is aft of LCB, then the after draft increases. Moment to trim 1 inch, or MT1, is the moment to change the trim of a vessel by 1 inch. In the metric system, this is the moment to trim 1 centimeter, or MTC. These final concepts are the core of ship stability and trim. Every officer needs a working knowledge of these terms in order to understand the stability of their vessel. Heel is the angle a ship assumes as a result of an outside force, such as wind or waves. Unlike heel, a vessel is said to list if it is resting in the water at an angle without an outside influence. Normally, this is due to what is called an asymmetrical load, an uneven load that causes a vessel's center of gravity to move off of the center line. A list should be quickly and easily corrected. As we've seen, when a vessel rolls, B moves in the direction of the roll and out from under G. The metacenter, or M, is the intersection of the upward force of B when a vessel is upright and when it is at an angle. Think of it as the center of the arc that B moves through as a vessel rolls in the water, like the anchoring point of a pendulum. It is considered to be on the center line at small angles of heel. The location of the metacenter is provided for the ship's officers by the naval architect and is a key value in calculating stability. The vertical distance between the center of buoyancy and the metacenter is called the metacentric radius, or BM. Once there is a horizontal distance between the center of gravity and the metacentric radius, the opposing forces of gravity and buoyancy create a righting moment that returns the vessel to its upright position. This horizontal distance is called the righting arm, or GZ. The righting moment, the rotational force that rights the ship, is the length of the righting arm multiplied by the vessel's total displacement. Km is the vertical position of M, measured upward from the keel. Metacentric height, or GM, is the vertical distance between G and M. When we put these things together, we see the ship's stability triangle. This shows us that the larger the GM is, the longer the righting arm, or GZ, will be. The longer the righting arm is, the greater the force of the righting moment will be, and the ship will have a greater ability to right itself. For this reason, GM is used as the standard measure of a ship's initial stability. This is the stability for small angles of heel, usually less than 7 or 10 degrees. When a ship heels any more than that, its metacenter moves off of the center line and stability becomes a more complex problem. Initial stability is still used as the standard measure of a vessel's stability, however, because if a vessel has enough initial stability, it is believed to have sufficient stability for larger angles of roll. Knowing the fundamentals and terminology of stability is just the beginning. Once you're comfortable with the terms of stability, you can begin to understand the stability calculations required of every officer. As you continue to study stability, you will become familiar with the hydrostatic tables provided for your ship and use them to help you find its required stability. You will use initial stability to determine your ship's overall stability, as well as range of stability, maximum righting arm, and danger angle. Understanding the stability of your ship is the key to making every voyage a safe one.